Look, it's a tower which goes into a spine beam, and we wanted really to try and keep that whole structure fluid in one piece of steelwork. Then the deck is cantilevering off the spine beam, which runs down the middle of the bridge, and we've got a nice edge beam which makes the deck look really beautiful from the side. And we've got 4 cables which are in the plane, a single plane of cables, which then connect the spine beam to the tower.
So the structural form is a little unusual in that it's a cable stayed structure without any backspans, and that, you know, I think we hopefully explained within our submission that the structural form is very much driven by the need to limit the time and the disruption that we spent on site, so that we could maintain the existing structure for as long as possible. So the fact that the bridge had no backstays, that the stiffness from so the cables want to pull the pylon over, the pylon has to be stiff enough to transfer that force into the foundations. Transferred be a pile cap, and then quite a large ring beam and 600 diameter piles that take the force through that sort of historical quay wall down to a rock shelf. And that rock shelf was actually the sides of the old channel that used to actually come into the harbor. So that where the cut is actually a natural entrance into the bay that was then built up over time. And our foundations go down onto that rock shelf. And what that meant was the bridge could be built off-site, brought onto site and erected fairly quickly, without the need to construct back anchors and backstays, etc. And as Maya said, the design, the structural design was very much to create a single form, integrated form, that was recognizable as a landmark for the V&A.
Great. What were some of the challenges that you had, and how did you overcome them?
Well, I think obviously the biggest challenge of the project was to keep the cut and the existing bridge operational for as long as possible. That was critical for the V&A. It was probably one of the top priorities. And then the other priority for them was although the bridge was going to be double the width, it had to operate at the same speed. We had various people look at the bridge over time, and they were amazed at the existing bridge, how quickly it opened and closed. And the V&A was used to that high level of service. So the other sort of challenging aspect was to double the size of the bridge, but to keep the operational speed the same. So the end result was that the existing bridge, while the existing bridge remained operational, we actually adjusted the swing of the existing bridge so that we could build an abutment on the clock tower side. So we reduced the rotation of the bridge and built a temporary abutment so that the existing bridge could keep going throughout the construction of all of the substructure elements. So the substructure was built while the existing bridge remained operational, and then the design intent was that the new bridge could essentially be fabricated, built off-site, and then floated into position and lifted up and installed within a couple of weeks. So the existing bridge remained up until the final month of the construction stage, and only in the final month did we bring the superstructure on, install the slew bearing, and place the new bridge onto it. So that drove the conceptual design, and it took quite a bit of iteration to come up with a practical scheme and a safe scheme for the V&A. I think one of the biggest challenges was piling through the technical challenges was the construction of the substructure, because the existing bridge just sat lightly on the quayside. It had no piled foundations, but doubling the size meant we had to double the size. And we were dealing with a sort of unknown quantity, this historic quay wall, which was essentially, you know, packed rocks. It wasn't an engineered structure with the facing. So the big challenge was not to damage the quay wall, not to damage any of the adjacent buildings, because we were dealing with an unknown process. Maya, maybe you can just describe that the process that was followed on the foundations.
Yeah. So as John was saying, the quay side is really just rocks that were placed there when they built up the channel. So the channel, as John mentioned at the beginning, was an existing channel and a natural channel. But when they started using the harbour for bigger boats, they needed to deepen that harbour and make that channel more pronounced. So they blasted the channel deeper and they built the quay wall, and they really just dredged rocks and threw it behind the quay wall, which was just a packed stone wall. So the rocks behind there are just loose, nothing's holding them. What we were worried about with I actually remember the geotechnical engineering describing that wall just as a pile of marbles. And the concern with piling was that as we would start to pile, we would dislodge some of those rocks with vibration and the air that was being blown through and the stones that would be thrown up. So the idea was to first do a pilot hole with just a small core, and then we grouted those up to actually bleed grout into the surrounding stones to hold those stones together, so that when we came with the much larger pile rig and bored through the stones and the rocks that make up that quay side, it then would hold everything together, and that worked quite successfully. So we were happy with how that all ended.
Great. Can you give us a little bit more detail on the actual fabrication and erection process in terms of complexity or how that went?
Yeah. So the conceptual design is an upstand beam, because the bridge has to swing onto the quay wall. So we couldn't have a downstand beam. We had an upstand beam, and then we had the deck cantilevering from the soffit of that upstand beam. And then the tower, the pylon, is a continuity of the upstand beam. So that's one single element. And it has to be a box because it's a central spine beam. It has to take torsional loads, so it has to have a torsional stiffness. So we were essentially dealing with a box construction. So the normal challenges that exist were there in terms of coming up with a plate assembly that was practical to assemble and to joint on site, that all welds were accessible and practical within that assembly process. And because it's a cable stay bridge, the bridge is subject to quite large compressive forces. So there was quite a bit of effort had to go in to check the local buckling of those plate elements for both the erection loads and for the structure in its permanent state, and especially in the pylon, which is obviously the cables go up. There's a large compressive force going down that tower. We needed an arrangement of internal stiffness to prevent local buckling. And again, just the continuity of those stiffeners and the welding sequence that goes with it had to be quite carefully thought through. Even in the design stage, that what we were putting on the drawings was practical, so that when you needed to essentially ensure that you had continuity between two elements that were joining together, continuity between those internal stiffeners, that you had access to weld those joints, those internal elements. So we actually, from the very beginning, we decided we would develop from our side in the design office, the project in Revit. So every element of the bridge was developed in 3D, and every element and that sequence of plate assembly was checked, and that sequence of access to internal steel elements was checked. We have lighting assemblies, we have video cameras, we have wind sensors, we have navigation lighting on the bridge. So all of those services are internal within the box, and again, the jointing and the accessibility of those services was tested with Revit. Obviously, the fabrication happened mainly in a yard out near the Cape Town airport, and we basically detailed the bridge into sort of 3 assemblies that could be transported to the V&A. So those assemblies were fabricated in the yard. When they were complete and 80% of the painting done, they were transported to a jetty at the V&A, and then they were essentially spliced together. So the spine beam and the pylon was then created, then the deck sections were brought in, and actually all those were detailed with bolted connections just to reduce the amount of welding that we would have to do out in the open on the jetty. But yeah, so I think the big difference for on a project like this is the fact that it's a moving bridge, and the fact that it has to integrate with many mechanical parts. There's a nose pin that essentially locks the nose in place on the far abutment. The bridge has to transfer all its forces from the beam and the pylon down into this big radial ring beam that then sits on top of this slew bearing, which is essentially just a big, large turntable that's driven by the hydraulic motors. And those slew bearings are extremely sensitive to point loads. Any sort of small deformation can affect the friction within that slew bearing. So we had to essentially design that ring beam such that it would distribute the load and would also limit the deflection to, in the substructure and the substrate supporting the slew bearing to less than 1 millimeter. So we used the slew bearing in a slightly unconventional way. Usually slew bearings sit on cranes or types of machinery where the load is evenly distributed around the full perimeter of the slew bearing. In our instance, we had a spine beam that essentially crossed the slew bearing in 2 places. So we had to come up with this, as I say, this very deep, stiff ring beam to try and distribute that force onto the slew bearing. So there was quite a lot of effort went into that connection point between the structure and into the mechanical aspects of the bridge.
Great. So just our judges, are there any extra questions that you'd like to ask before I move on to how he feels that the benefits of steel are illustrated in this project?
Sorry, can I just complete the
yeah,
sort
sure,
of,
go for it.
So obviously, as John described, we fabricated the whole bridge together on the jetty, and then I guess the big engineering exciting part of the erection process was then to pick the bridge up and put it onto a barge, because this jetty was actually just a little way away from where the bridge would be placed in its final position. So on the night before we put the bridge into position, we lifted it up and put it on the barge, and then early the next morning the barge brought the bridge to site, which is just a couple 100 meters down the way. And we then again had to pick up the bridge from the land, a single crane picking up the bridge and placing it onto the slew bearing that John's been describing. So I think the challenge there with that erection was the slew bearing had a number of bolts that kept coming up out of the ground, a whole lot of holding down bolts. And we have to, essentially lift and place the bridge down onto that over these 34 bolts. And that obviously was quite a challenge to make sure that everything was lined up correctly. the tolerance had to be very small, and to make sure the flatness of that slew bearing between the slew bearing and the bridge was really as flat as it needed to be for the sake of the slew bearing, we needed to epoxy between the two. So what they actually did is they picked up the bridge off the barge, put it down into position to make sure it could go. Then they lifted it up ever so slightly and painted on an epoxy. And that was a really time sensitive operation, because it had to be done with, I think, John, I'm sorry, I can't remember the time limit, but it was, a minute or two. It was a really small amount of time. And then the whole bridge had to be brought down again into its final position. So it was quite a busy day for the crane operators and the erection engineers to get that into position.
Great. So, judges, are there any other questions, or can I move on?
Yeah, Denise. Good morning, John. It's Spencer.
Hello, Spencer. How are you?
Very good, and you?
No, well.
I see a few more grey hairs.
Yeah, and less hair.
Sorry about that. What sort of plate thicknesses were we talking about on the boxes?
On the boxes, it was relatively, it was 20 mil and 25 mil on the spine beam and the pylon, but the ring beam you were looking at up to 60 mil plate, and as Maya said, machine finishes to get the tolerances on the slew bearing.
Yeah. And what welding spec was the work done to?
AWS D1.1.
Okay.
So it was you've given us a few good people to talk to over the years, Spencer. So
Great stuff. Thank you, John.
Yeah.
Okay, great. I want to just maybe move on to the questions for Ian and for the architects. So, Ian, can you give us a little bit of a description of what the actual brief for the structure was from the client? You're on mute.
You guys are on mute.
Don't worry, we do it all the time.
We all do it all the time, yeah. So obviously there were the practical issues around widening the walkway to, because of the pedestrian increased capacity of the waterfront, and the closing speeds that John spoke about, and then sort of more practical issues about reliability and the maintenance and the materials we selected. But in terms of sort of our contribution, a lot of the brief came in terms of the context and how it would fit within the waterfront. And there's a lot of historical buildings within there, and then there's also a lot of modern architecture of the waterfront. And probably the biggest influence is the nautical aspect. It's a working harbor, and wherever you look, you're seeing all these nautical references, which we took as a strong cue in the design of the aesthetic of the bridge. Yeah, I think, and when you factor in the waterfront, there's a whole lot of urban design aspects, like where's this bridge going to be seen from, what's the pedestrian movement, how do they access it? So that was all a factor. And then also the fact that this bridge would deal with sort of a mass amount of people, but when it opened and closed, they would gather on the one side and then they would move over the bridge in sort of big platoons. And how would we deal with that? Yeah, so that was essentially the brief, but the most important, how it fitted within the context of the waterfront, and ultimately it would become a landmark, almost a potential destination. We've seen that with other bridges around the world, and how would it form this landmark for the Cape Town waterfront?
So why steel, and how did steel play a role in achieving this specific vision, and why not another material?
So if we go back to that concept, we obviously didn't, the original bridge had, it sort of fitted within the historical building context. Like we said, it almost had like a Victorian element. There were a lot of cables. And when we picked up on that nautical theme, we started looking at sort of yacht design in general. Multiple sails, multiple stays. It was actually quite a complicated structure. And then if you look at where yacht design's gone now, especially those like trimaran yachts, the sail is one single element and the hull is one single element, and they kind of combine the two, so it's just a single form. So with us in this single mast, we wanted to try and keep that in the aesthetic, and that's what steel allows. It's this one single element that we're able to shape, and obviously we use computer modeling, and we sort of have a drawing and it turns into this computer model. But steel, because of its high strength to weight ratio, we can actually keep it slender, keep it slick, and give us that aesthetic. Yeah, so that's why it's good.
Awesome. So just a question. Okay, I see someone raising their hand there. Go for it.
Yeah, Denise, just on the why steel question, there's quite a lot of, why steel was the chosen material. Obviously with the moving bridge, the weight of the structure dictates the power required to move it. So, having a relatively lightweight structure was important. As Ian says, the strength to weight ratio of steel is ideal for that. We did, we obviously in preliminary design, we have to look at all sorts of options, but the only real options were steel and perhaps, these glass fiber structures. There are a few examples of those around, and even in boat building technology, there's a lot of reinforced polymer or fiber structures out there. But in the end, what we have capacity, expertise, especially in Cape Town in steel structures. We're very lucky in the fabricators we have here. And in the end, the steel offered the strength to weight requirement that we needed to limit the power requirements, and it also we knew we had the skills in Cape Town to deliver a complex structure using steel. And then, as Ian said,
the proven durability.
Yeah, the durability, the fact that it's well codified, all of those gave us a high level of confidence in using steel as a material, whereas the others not so much. It's very much a proven material for us in building bridges, and we know what we're doing in terms of fatigue and all the critical design issues. And as a moving bridge, it's a different thing. There's you've got a lot of dynamic forces going on. You need a high level of certainty and a high level of safety when designing these type of bridges. And then, as Ian said, with steel, you conceptually, the page is open. You can almost design what you want to. So it gives us as designers this huge amount of freedom to create something that's not a collection of beams and columns. It's a unique element in itself. As Ian says, it's got its own identity. It's not a collection of parts. It's the V&A Waterfront Bridge. It's the only one. Yeah.
That kind of leads into my final question, and then I'll open it up and see if the judges have got any other questions. Is what are you as project team members most proud of on this particular project?
Should I go first?
Go for it. Yeah.
Look, well, I mean, I'm proud of how it works. For one, I mean, it really, it's just functionally, it works very well. But I think for me, it looks very simple and very timeless. And for things to look simple, it's actually a lot harder than you think. The more simple something looks, it takes an entire team, quite a in-depth creative process to make something look that simple. And I also think it's timeless. It's going to stand the test of time in that waterfront. It looks good now, but I think it's going to look good in the years to come.
Maya, what do you think?
Yeah, I think also just leading on from what Ian's saying, I think what's quite impressive about the bridge is that so much of the hard work that it's doing is hidden. I think when people see the bridge, they just see this very simple, slender mast and beam, whereas there's actually a lot going on, just below the surface of the ground there, all the moving parts that are hidden. Even as John was saying, all the things that we've got going on in the bridge, the cabling and the cameras and the wind and all of that we've managed to kind of tuck all those things away so that you're just left with this, simple like form. And yeah, I think it looks good. So I think we're all proud of how well it can function without actually kind of, it's all kind of tucked away and hidden, and it's a bit of a mystery.
I think that's one of the nicest compliments we've had, is that somebody was surprised it moved. They walked across it, they never saw it. But for us as bridge engineers, we like this idea of the ground continuing. So one of the nice aspects of it, a lot of effort went into the approaches and the urban design around the approaches. So that as you approach the bridge, it's just the ground rising up and you're crossing the bridge. And as Maya says, there's a lot going on that's essentially unseen. But I think for me, we started this project, I think, back in 2016, and for everyone, they've recognized, creating a new structure on the waterfront is a great opportunity. So there's been a lot of tenacity in keeping the project going and getting it to the point where, we managed to get funding, and there've been, hiccups along the way in terms of that aspect of things. And, we've had multiple contracts to manage the fact that the substructure's been built separately, then the superstructure to manage the disruption to the V&A. So it's been a long process. But I think the unique aspect of moving bridges is that it involves so many different people. And I think one of the big highlights is, as Maya says, is you create this seamless thing that works and operates, but behind it, you've had so much collaboration between so many different parties. We've had heritage engineers, we've had obviously mechanical engineers and electrical engineers from the UK helping us. We've had architects, we've had urban designers, we've had landscape designers, we've had the V&A's input. For a lot of this process, we've collaborated very closely with the contractor. We even at one point tried to get an alliance to build the bridge. But, so that coming together, that collaboration to create one certain thing has been quite amazing, just in terms of the number of people that have come together to put this thing, to make this thing happen. And I think, it's been done I think because of the location, because of the nature of the structure, everyone has been extremely positive and proactive in problem solving. So it's just been a very nice experience for everyone.
That's fantastic. I just want to let you know we've got 4 minutes
Sorry.
left. So Spencer, if you just want to ask your question, I see Emmanuel also has his hand raised.
I just wanted to make a comment. Maya, I think your adjective using the word simple just doesn't do justice to the bridge. I think it looks stunning, and I think I would have rather used the words clean lines or apparent simplicity, but not simple, please.
Okay.
It's great.
Thanks. Sorry.
Okay, Emmanuel, do you want to go ahead there? We've got 3 minutes left.
Okay, yeah, sorry, I may have missed this as I came in a bit late. Yeah, it looks spectacular. 2 questions. One is, how is the bridge powered? And 2, is there any monitoring going on? I'm thinking maybe from a structural point of view now. Stuff to monitor as the bridge progresses. It could be in terms of fatigue or vibration or some other stuff, mechanical parts. There's 2 questions.
So it's powered by a set of hydraulic motors, which is the preferred choice in a marine environment. But the power is coming from the V&A itself. We actually used the pit room for the old bridge to house the controls for the new bridge. So the substructure from the old bridge is being used unhidden below the ground. And that's where all the machinery, the controls for the hydraulic motors, but it's powered electrically, and it's got hydraulic motors to drive, 4 hydraulic motors to drive that slew bearing at the speed that it's needed to. Just in
If we,
terms
if
of
we do
the,
suddenly cut off, please don't be alarmed. If any questions are unanswered, they can be answered via email. I'm also mindful that Kevin had a question quickly, and we are going to probably cut off in about 2 minutes.
okay, sorry.
Kevin, you want to go ahead?
Yes, thanks, Denise. I think you guys have done an amazing thing, and it's so great for us to see something other than a portal-shaped industrial structure. So well done. It's really amazing. My question is more around fabrication, and I wanted to ask what grade of steel was used in the bridge predominantly.
Yeah, so it's predominantly 355. I think it's J2, just because it's a bridge. Yeah.
Okay, so the first part of that is there's a lot of limitations on the availability of special grade of steel like J2. And as far as the size of the parent sheets are concerned, how did you decide where to put the joins of sheets? Because presumably the parts on the bridge are larger than the available sheets. So how did you decide where to join steel and manage that part of the fabrication process?
Because it's a box and the dimensions of the box are not that large, it wasn't really a problem that came back to us as a design team. I mean, our intent was around the sequence of putting it together to make sure that any joint that you had, you could access. So if it was a plate, it was easy enough to access that through the construction sequence. So, in terms of looking at the limitations, our thought was always around access, because we knew we would finish the box and paint the box so that the joints themselves wouldn't be that transparent. And we also have this overhang that we use to create the visual continuity, because the box is faceted as it transitions from the pylon to the deck. But we had this cap that we used to give the smooth visual continuity, and that also provided us with the lighting to hide some of the joints as well. So
right, folks,
it allowed us.
I think. Sorry, we're going to cut off. I'm just if